Hello, everyone. Can you guys hear me? Is this clear enough? Yeah? Good, good. Sort of? There's some hands going up there. Louder. All right. Can this go louder? Oh. Can this go louder? Yeah, they'll sort that out. In the meanwhile, I'll continue talking. You know what? It was actually more crowded earlier. I mean, I thought all those guys were here to see me. Apparently, they were here for some stupid book prize draw thing. Anyway, how's everyone doing? You all feeling kind of sleepy after lunch? I kind of ate a bit too much and, kind of dozing off in the corner. That guy's dozing off. All right. So my name is Manik Surtani. I'm a platform architect at Red Hat. I work in the JBoss division of Red Hat, and this is where we do a lot of middleware. Is everyone here familiar with JBoss? Does everyone know what JBoss is? Yeah, good, good. Because I'm not really going to go into too much detail there. And I'm going to talk about the JBoss Data Grid. Now, the JBoss Data Grid is a fairly new product that we've come up with. It's based on Infinispan. Now, who's heard of Infinispan here? Any hands? OK, not many. That's fine. I'm going to talk about Infinispan primarily in this talk. Before I start, though, I'm going to give you guys the difference between JBoss Data Grid and Infinispan. It's more or less the same thing. It is pretty much the same code base. The only real difference is that the JBoss Data Grid is the productized version of Infinispan. This is the version that we recommend for enterprise use. This is the version that you can buy support on, you can get consulting on, and things like that. While Infinispan is the upstream open source thing with more experimental, if you will. It's a faster moving branch. You're all familiar with Red Hat and Fedora, the difference between RHEL and Fedora, right? Two different forms of Linux. It's pretty much the same thing. That's the same sort of difference here. So just kind of getting into things, why are data grids interesting? Firstly, well, mainly, there's a lot of data out there today, right? And that amount of data is just increasing. There's several reasons why, and I'm going to talk about that. But the biggest and the most interesting thing right now is I think that the whole problem of data growth and having a lot of data out there is so mainstream that even business magazines are using the term big data all the time. I mean, who's ever seen, there was an article in The Economist a couple of months ago on big data. It's like, seriously? Big data is like a technical thing. It's meant to be something for computer scientists. Why is The Economist writing about big data, right? I mean, it's becoming pretty mainstream. It's a mainstream problem, and everyone knows about it, and everyone needs to deal with it. So that's why it's interesting. There are a couple of reasons why it's become mainstream, a couple of enablers. One is the cost of storage. Cost of storage is becoming cheaper and cheaper, ever so. So if you have more space to store things, you may as well store things. The cost of processing and bandwidth dramatically lower as well. High-speed mobile networks and smartphones, that is another very big enabler, and I'll explain why in just a minute. And there are a couple of other drivers as well. So since I touched on the smartphone thing, let's talk about that. There are a lot of things out there now that are generating data. Right? In the past, there weren't that many connected devices that are always on. Today, we live in an era with smartphones that are always connected to the internet, that are always capturing data and always generating data. Right? Things like GPS is on your smartphone, tracking where you are. You got little devices, those Nike devices that you put in your shoe when you go jogging, that kind of tracks where you've been and how fast you've been running and how many calories you've burnt, and all that is then sent up to your account in the cloud. So I mean, it's constantly moving data around. So there's a lot of data out there. Even things like electric cars, which are now becoming popular in certain countries, again use a lot of tracking data to monitor how the batteries are behaving and things like that. Things like smart thermostats and home automation, again, getting popular in some countries. It's going to get even more popular as we move forward, where you can control the heating at home when you're still at the office to make sure your home's nice and warm when you get there in the winter and things like that. The next thing is the cultural shift. The rising middle class, some of the biggest countries in the world, means that more people can afford more devices and be online all the time, right? The current data explosion we are seeing is primarily driven by Western Europe and America. This is going to change very, very significantly. There'll be a lot more data as more people get online around the world, as more people are always connected using smartphones and things like that. And of course, businesses want to do something about that. They need to harness all this data, right? I mean, if you're running a business, whether it's a startup or whether it's an established business, you know that there's a lot of data out there. You know there are things you can do with it. There are things you can do to make your business better and faster and smarter. So you want to be able to store it and capture it, right? Like I said, now storage is cheap, so we can store it all. So now how do we actually process it? How do we deal with it? How do we make sense of it, right? And also all this has to be fast as well. When you're capturing data, you can't expect to have long lags to sit and store stuff in big complex data warehouses. It's got to be very fast, low latency. People have very short attention spans, things like that. So essentially what we're seeing at the moment, what's happening is that, I mean, this quote comes from some very smart people at some analyst company, and they talk about a new generation of technologies designed to extract value from this very, very large amount of data, right? By capturing it in a very fast manner, discovering and analysis in real time, and stuff like that. Now, there are a lot of tools already available to do this, and this is where things are going to start getting interesting. The first one we're all kind of familiar with, that is cloud, right? We all kind of know what cloud is, right? There can't be anyone in this room who's not familiar with the term, right? Is there anyone who doesn't know what cloud is? Really? No? Right. I didn't think so. Right. So we all know what it is. We all know why cloud is a good thing as well. You get elastic provisioning. It's dynamic. As you need more capacity, you can spin up more nodes. You can shut down nodes when you don't need them anymore. So economically, it's very viable. It means that even as a small startup, you have access to a large amount of computing power. You have access to a large amount of storage on demand and stuff like that. So it's all very cool. So cloud kind of helps, is one tool we already have now to help deal with the big data problem. The second thing is data grids, and this is where I'm going to talk about this specifically. The bulk of the talk is going to be focused on data grids and why data grids are important in this space, how you could use them, how they actually work, the nuts and bolts behind it. And I'm specifically going to be talking about the JBoss data grid or Infinispan. And I'm going to use that as an example. So firstly, what are data grids? Who actually knows what they are? Who can definitely say they know exactly what they are? It's kind of a hard term to pin down. A lot of people say, yep, that's a data grid, and a different vendor will give you something completely different and say that's a data grid. It's a kind of a loose term. It's not been properly nailed down yet. So whatever I say here is really just my opinion. A data grid is an evolution of a distributed cache. So you usually start with something like a single cache and a single VM. You realize that's not enough. You then have your application running in a cluster. You now have to distribute your cache across a cluster, end up with a distributed cache. But still, that's just very basic. It's just storing objects in memory and retrieving objects from memory. Kind of simple. A data grid is a few steps further. You then take it and you add more processing capabilities, things like MapReduce on the data set in memory, the ability to perform queries on your data set in memory, the ability to actually persist this data set onto disk as well. So it's not always in memory. So you can survive restarts, you can survive node failure, you can actually address a larger data set that's even more than the memory you have. Like I said, disk is cheap, right? You can put lots of extra disk space and offload things onto disk as well. Now, data grids are a pretty well-known pattern to boost performance, right? It's been used time and time again over the last 10 years at least to make databases go faster. Quite often, a database is your biggest bottleneck in most applications. It's your biggest bottleneck because touching disk is expensive. Every time you go down to disk, it's expensive. Quite often, a relational database also sits remotely from your application server, which means you're connecting over the network to get to a remote disk, so on and so forth. It becomes expensive. So a lot of people have used data grids in front of your database, in front of your relational database, to make things run faster. It makes your reads more scalable. If you can write to the database asynchronously, it makes your writes more scalable as well. So it's a well-known pattern, well-understood pattern. But that's just historic stuff, right? I mean, gradually what we see is more and more people now have that data grid in front of the database and realize, hang on, what if we just remove that database altogether? Do we actually need that there anymore? Right? And run everything out of the grid. So that's becoming an interesting pattern now. Kind of in line with what a lot of the NoSQL people are doing in key value stores. Very, very similar sort of thing. Now, one of the good things about data grids is that they are distributed by nature, right? They're very, by design, like I said, they come from distributed caches, so they are clustered by nature. The very fact that you have a data grid means it is clustered, and that gives you a lot of cool things for free. For example, it gives you the fact that your grid is fault tolerant. If one node were to fail, your application's not gone away, your data's not gone away. It's still there on the other nodes, right? So you get fault tolerance for free. The other thing you get for free is elasticity, which again is very important. The ability to add more servers to that grid and to cope with more load without shutting anything down. So if you start with 5 servers and realize after a while that 5 servers aren't enough, you can bring some more servers up and have them all join that grid, and you have more capacity, more storage capacity, more processing capacity, and then you realize after a while you don't need so many servers anymore. You can shut some of them down, again, without shutting the entire system down. The entire system still continues running. So you get elasticity for free. That's, again, very cool. And as an offshoot, you end up having a very, very scalable system because you can scale out and back down very easily, which you can't really do with a database, with a relational database. Well, you can, but it's very, very difficult and expensive to do. So a little bit about the JBoss data grid specifically. I mean, all that stuff I just said, that's just generic stuff about data grids. The JBoss data grid is very much a data grid. Does all the stuff I just spoke about. It is distributed. It's in memory. It's a NoSQL data store. It stores things in key value pairs. It is elastic and highly available. One of the other things that the JBoss data grid is, which is not something I would say all data grids are, is it's manageable. In that, what I mean by manageable is JBoss does a number of things in middleware. So we sell app servers, we've got message queues, transaction managers, things like that. And we have a single management console to administer and manage your entire infrastructure. And the JBoss data grid is manageable as well through that same admin console, which is great. It means that you get to see your entire data grid in one web-based console. You can fire up more nodes, shut down nodes. You get alerts as to what's happening on each node. It's all pretty cool stuff from an operational point of view. And like I said, JBoss data grid is built on top of Infinispan, which is the open source version of it. Well, they're both open source, really, the upstream version of it, if you will. A little bit about Infinispan. It's been around for a while. It's been in active development for about 3 years. Who's heard of JBoss Cache here? A couple of hands. Right. So I used to be the project lead in JBoss Cache once upon a time. And I found that a lot of people started using JBoss Cache as a data grid, and it wasn't really designed to do that. JBoss Cache was designed as a very simple distributed cache, mainly for the JBoss app server to cluster HTTP sessions. So a very, very simple use case. But people started stressing it and using it in lots of different ways, and we figured, you know what, that's actually pretty cool. We can actually build something to do that with a few changes to the core design, and that's where Infinispan came from. So we built Infinispan from scratch with the sole purpose of being that distributed data grid, that distributed NoSQL key value store. It's been going around for a while now, so like I said, about 3 years ago, that's when we started. Pretty active development. We've got a pretty big community right now. The community, when I say community, I'm not just talking about people who develop on it or who build it, but the community includes people who help writing examples, tutorials, documentation, end users. There are people who OEM it and rebrand it and package and sell it. There are some guys who are actually embedding it into little devices as well for certain applications and selling devices with it embedded on it. So there's a lot of cool stuff going on. It is a very active community, and if anyone's interested, I'd recommend you join. I'll have some links at the end with some details as to how you can join the community. Now, one thing interesting about the Infinispan community, and this has nothing to do with open source, but more of a style of project management, if you will. The way I run the project is everything, even internal meetings with core developers, is all in public. Everything happens in public IRC. We have a fixed schedule. We meet once a week on a Monday afternoon, European time. And that's where we have our meetings, and developers from all over the world can join in. Anyone in the community can join in. Anyone can listen, anyone can see. There are no secrets. Everything is kept in the open. And this is what I call true open source. It's not just the code that's open. It's the processes and what we're doing. Everything is open. So again, if anyone's interested, feel free to join in. One other thing I'd like to mention with regards to Infinispan and the JBoss data grid is CloudTM. CloudTM is an EU-funded project. It came about a couple of years ago. It started as, it was mandated by the EU that they wanted to build this scalable platform for the cloud, a data platform for the cloud, a little bit like software transactional memory, STM, hence the name CloudTM, cloud transactional memory, except that the memory is distributed across cloud nodes. Now, STM is a very interesting concept for single VMs, for single servers. It's kind of hard to implement something like STM across in a distributed fashion. So this is what this research group was all about. Now, I actually represent Red Hat on the CloudTM consortium. A couple of other interesting entities there is the University of Rome and the University of Lisbon, the research departments from these two universities. They've got a pretty active distributed computing section within these departments. There are a couple of PhD students there working pretty hard on this stuff, getting their PhDs on it, and some really, really cool research is going on in this area. Now, one of the cool things they're doing is they've actually forked, they maintain their own fork of Infinispan, where they're putting in like really bleeding edge, really cool new algorithms and really cool new things. And as that matures, I then pull it back into the mainstream Infinispan, and then eventually into JBoss Data Grid. So this is one of our hotbeds of research, in a sense, where some really cool new research is coming in. For example, one of the things we're doing is, so who's familiar with transactions? Everyone knows what transactions are, right? What JTA transactions are, right? Two-phase commit, right? You know what two-phase commit is. So, and that's kind of clunky, right? I mean, you know, you've got a prepare phase, you've got a commit phase. If you're running in a single machine, that's not so bad, but if you're running in a distributed environment, that quickly becomes like a lot of network noise, you know, trying to coordinate things between different servers, it becomes quite complicated. Now, Infinispan's got a pretty efficient, pretty advanced two-phase commit implementation, so it works pretty well and it scales pretty well, but with these guys, we've been implementing a whole new series of protocols that can replace two-phase commit in a single phase. It'll give you all the same guarantees as two-phase commit, but it'll run in a single phase. And it works on techniques like network ordering of messages, of UDP packets, and things like that, to give you the same kind of guarantees. It's called total order broadcasts, and things like that. So very cool stuff. One of the other interesting things coming out of this project is data migration. Now, I'll explain later on about how Infinispan works and how Infinispan stores data and selects which nodes to store data on. But they're working on ways to dynamically migrate data across the cluster as well to keep it close to where it's needed most. And that, again, is very interesting. So it does auto-collocation, if you will. So if the system sees that these two servers are always using particular pieces of data and the other servers aren't using it that much, it'll try and move the data there and keep it there permanently. Again, so things are local as much as possible. Again, improving performance quite a lot. A couple of other interesting things, autonomous configuration. So with all distributed computing systems, one of the most difficult things for an end user or developer to do is to configure and set it up, right? It's pretty complex, right? You got a whole bunch of network protocols to deal with. You got a whole bunch of things regarding thread pools and sizing and whatever to deal with. It's not simple. So one of the things, again, coming out of this project is an autonomous manager to monitor your existing system and dynamically reconfigure things at runtime to give you optimal performance based on what it sees and how you're running it. So again, that's some very cool stuff coming out of that as well. So enough about CloudTM. Let's talk a little bit about standards as well. So I presume everyone here is a Java person, right? You're familiar with the JCP, right? Yes? Yes, good, good. Who's heard of these two JSRs? So JSR 107 has got a very interesting, very dubious accolade of being the longest standing JSR that's still in existence. It's actually about 10 years old, and I'm actually on the expert group of JSR 107. JSR 107, a very simple JSR to provide a temporary caching API for Java in a standard way. In a sense, a standard API that you can use things like Infinispan or Coherence and EHCache and Memcached and everything else in one standard way, and swap providers in and out. This JSR, thankfully, is finally close to completion. Despite being around for about 10 years and still not getting very far. It's finally close to completion. It's going to be a part of Java EE 7. So it is actually going to be included in any Java EE 7 compliant app server. And Infinispan is JSR 107 compliant, or it will be once 107 actually completes anyway, because it's still a draft. It's still in final draft. JSR 347 is a new JSR that I'm the spec lead of JSR 347. I've just recently proposed it to Oracle. This is an API for data grids. So it takes the JSR 107 API and extends it. It adds a few more things to it. JSR 107 is quite a simple standard, quite a simple API. It just does put, get, remove, stuff you'd expect a cache to do. It's got standard ways of defining eviction. It's got standard ways of defining write through and write behind to disk, but nothing more than that. So JSR 107 is quite simple. JSR 347 adds a lot more to it. It adds things like MapReduce, queryability, asynchronous operations, even eventual consistency. So things that are very interesting for distributed systems for data grids, and that's all going to be in 347. Now, again, a quick note about 347. It's a very young JSR. It's quite new. So all the stuff I said may not even be there in the end, but I hope it will. We're still working it out. One of the things with JSR 347 is the way I'm running it. Now, again, has anyone here participated in a JSR before? No? Well, let me tell you what, it is horrible. It's really, really difficult to do, right? You've got to go and get become a part of the JCP, and then you've got to go and write into the JCP saying, I'd like to participate in this JSR. And then the JCP will email everybody on that JSR and have everyone vote whether you're allowed in or not. And then once you go in, you realize, hang on, these guys have been talking about stuff for months, and I've not been a part of that, and no one's got any records of anything, so you can't catch up with anyone else. And it is a nightmare. The difference with 347 is, I mean, I'm an open source guy. I'm doing this entire thing in the open again, where JSR 347 at the moment is nothing more than a GitHub account with some source code in it, and a Google group, which is open to anybody and everybody. And I'm basically kind of bypassing the JCP, saying anyone can participate in it. If anyone's interested, just sign up to the Google group and just tell us what you think. I don't want this to be a vendor-driven JSR. I think that sucks. There have been too many vendor-driven JSRs where vendors decide what you guys need and decides on a standard of what you guys need. That's bullshit. I mean, you guys know what you need. You should tell us what you need. And I'm kind of turning this around. So again, there'll be links at the end. Please do sign up. I'd like to hear what people think. Okay, so getting into a bit more detail now about Infinispan. Let's look at the core architecture. Infinispan is a data grid, so it's peer-to-peer. It's designed with a peer-to-peer model in mind. Who's heard of JGroups before? A few hands. So JGroups is essentially an open source peer-to-peer library, a peer-to-peer networking library. It provides facilities like auto-discovery of new servers coming on and servers leaving. It provides facilities like coordinating things between a cluster. So lots of cool stuff there that we get for free. Infinispan is built on top of JGroups. So we extend JGroups, we add extra things to it. We add the storage capabilities. We add the serialization capabilities and things like that on top of JGroups. One of the big differences with a peer-to-peer approach and some other data grids is that there is no single point of failure. Because everything is a pair, every node is equal. It doesn't matter if some nodes were to go away and other nodes were to join. There is no single point of failure. I mean, there are some other products where you end up having like a controller node or a name node or something like that, or one special node which cannot ever go down, because if it does, the entire grid is dead after that. Or then you've got to treat a separate cluster of servers or something like that, which just gets very complicated. Over here, every node is equal, so you get a high degree of fault tolerance, high degree of scalability, no single bottlenecks, anything like that. JGroups is pretty mature code. It's been around for like almost 10 years. It came out of academia originally. There were lots of papers written on JGroups, on group communication. The core JGroups team actually works for Red Hat as well, so we work very closely on this stuff. So that looking at JDG or Infinispan, it's the same here really. There are two different ways of using it. Right? The first one I'm going to talk about is what we call library mode, where what you effectively do is you have a bunch of jars, Infinispan jars, which you add to your project, and in your project you programmatically start an Infinispan instance. Very simple, that's all you do. Right? You provide a configuration file, or you can programmatically configure it using some beans, and then just start an instance. And then if you have another copy of your application running on a different server, like in that case a different JVM on a different server, do the same thing there, have another copy on another server, do it there, they will automatically discover one another, and they'll automatically start sharing data. So any data you put or retrieve in that instance is going to get copied there, it's going to get copied there, so anyone can see it, anyone can change it. If one node was to go away, the data is not lost, the data is now somewhere else. So you get all that very easily for free. This is effectively how a lot of application servers cluster themselves. This is how a lot of frameworks gain high availability and clusterability. This is in fact exactly what the JBoss application server does to cluster HTTP sessions. So when you fire an instance of JBoss AS7 and you start a web app there, and you know that your sessions are being stored there, and you start another instance of JBoss AS7 somewhere else, and you know that your sessions are being clustered, you can load balance across them. This is exactly what JBoss AS7 is doing. It's creating an Infinispan instance, and another Infinispan instance somewhere else, and they're sharing data. It's putting your session data in Infinispan. That's what's happening. So this is an interesting use case. This is how you use Infinispan in library mode. Now let's look at a degenerate case of that. Let's assume that you don't have a cluster anymore. You've only got one server. This is kind of useful as well, kind of interesting as well in a different sense. Over here, it's still a valid use case, still a valid usage mode. Here, Infinispan's acting as a fast JSR 107 compliant in-memory cache. That's it. Single VM cache, a bit like EH cache or something like that. That's what it's acting like. Maybe in front of a database, maybe in front of some other expensive data store where you're storing data in this memory cache. It's much better than trying to write your own cache. For example, it's a lot more rich than a map. It's got a lot more stuff in it than a map does. You get things like a far greater concurrency than even a concurrent map. You get JTA compatibility. You can be transactional. You can do things like warm starts. You can write through to disk. You can read from disk as well. All of this stuff happens transparently. If you try and implement all of that yourself, it's not that you can't, but you're effectively doing a lot of extra work instead of writing your application. Right. So all that was about library mode, but there is another way to use Infinispan as well, and that is in server mode. Now in this interesting case, you've got essentially Infinispan ships with a number of start scripts as well. So you don't actually have to use the jars directly. If you download the distribution, you've got a bin directory with a script to actually start it in the server mode, and that basically starts an instance of JDG. You do that in a few different servers in your cluster. Again, they will form a cluster. They will discover one another, start sharing data. But what it also does in this case is each instance opens a socket, and you can now talk to it from a remote client. Right. So your application now does not have to sit in the same machine on the same JVM as Infinispan, as your data grid. It can sit outside of your data grid. So you can treat your entire data grid cluster as one server or as one remote data store, a bit like a database. So it's one remote data store. Your application sits somewhere else, and you're talking to it. You're storing data in there. Your application can be in a separate JVM. It doesn't even have to be in a JVM at all. It could be a non-Java application. You could be writing something in C, as long as you know how to open a socket and talk to the data grid. That's it. I'll talk about the different clients we have as well. So when you're running in this mode, we support 3 different wire protocols. The first one is REST. It's a fairly simple wire protocol. Everyone knows how to use REST. You don't really need a client library for that. As long as your application platform knows how to open HTTP connections, that's all you need to do. Right? Very, very simple way of storing and retrieving data. A bit like what you do with say CouchDB. Right? Very simple. Fire a CouchDB instance. You're using REST to talk to it. It's that style of interaction. Very simple, very easy to use. You get the benefits of load balancing as well, because if you put a load balancer in front of your Infinispan cluster, it's all HTTP calls, and you can load balance across them. It's very cool, right? You can grow your cluster in the back end, you can shrink it, your application doesn't need to know about it. You get all the benefits of that. The next protocol that we support is Memcached. Memcached is a very, very popular single server cache daemon. Most Linux distributions ship with it. It's open source, it's free. But that's not the cool part about Memcached. I think the coolest part about Memcached is the wire protocol. It's got a very, very simple and easy to use wire protocol that pretty much anything can use. So we actually support the Memcached wire protocol when you want to talk to Infinispan. The benefit of this is that if you have an existing application that's using Memcached, you don't need to change anything. You just point it to an Infinispan cluster instead, it'll work. But the really cool thing is the fact that there are so many clients written for the Memcached wire protocol. There are clients written in pretty much any language in the planet, whether it's .NET or C, those are the easy ones, all the way through to Lua and Haskell and whatever. So I mean, even if you're doing something really crazy in a crazy language, you still probably have a Memcached client, which you can then use to talk to Infinispan. So you can use this data grid no matter what platform you use for your application. So that's pretty cool. The third endpoint, which is frankly what I'd recommend if you are using Infinispan in this client-server style, is Hot Rod. Hot Rod's a wire protocol that we came up with in the community for Infinispan specifically. We started with the Memcached protocol and added a few things to it. One of the biggest limitations of the Memcached protocol is that it's a one-way protocol. Clients can talk to servers, but that's it. The servers are treated as dumb instances in the Memcached protocol. And the reason for that is simple, because Memcached is a single server daemon. It's not meant to be clustered or distributed in the back end, so there's no need for that protocol to do anything more. But when you're using it with Infinispan, there is a lot more things we can do in the back end, and we'd rather do that. So Hot Rod allows, as a wire protocol, is a two-way protocol. It allows the servers to talk to clients as well. And that's very interesting. So if you have a client application talking to a set of servers, if that topology changes, if you have new servers added, the servers can tell the clients, hang on, there are a few more servers back here as well. You can now load balance to them too. And if some servers go away, again, you can dynamically inform the clients of that. So the clients don't need to be restarted or reconfigured or anything like that, which you have to do if you're using Memcached. But the other cool thing about Hot Rod is because it's a two-way protocol, the servers can also share the consistent hash algorithm it's using to distribute data in the back end. Now, this is important because if the server can do this in a reliable way, then the clients can be pretty smart about where it sends requests to the back end. It does not have to do a dumb load balancing and just going round robin in the back end, one server after the other. It could go directly to specific servers if it knows what data it's looking for, because it knows which server in the back end is the master copy. So it's much, much faster. One of the drawbacks of Hot Rod is it's quite new. Like I said, we only have client libraries for Java, Python, and Ruby so far. Excuse me. I think there's a C# client as well that someone's contributed, but that's pretty much, that's beta quality at the moment. I expect that to change over time. I expect to see more clients being written for Hot Rod. So the two different styles of communication here. Why would you? What are the pros and cons of each, right? Why would you run Infinispan as a server? Well, firstly, like I said, it sits outside of your application, and that's quite powerful. It means that you can manage those machines, you can manage those servers outside of your application tier. You can specially tune them to storing data. Give them more memory, for example. You don't need so much CPU power on those servers, you can just have more memory, and that's good enough. And for your application tier machines, you can configure them differently, having more CPU and things like that. Also, every time you restart your application, your data tier is not affected. Or if your application crashes, you're not taking down a data node as well, which is even worse, right? You can also share your data tier across different applications, just like you do with a database, where you have a single database and you have different applications talking to the same database. You can do that here in this case. And of course, your application does not need to be JVM based. Anything can talk over a socket, and that can use one of those protocols that I mentioned can be used. You're not just restricted to Java to use Infinispan. On the other hand, though, there are some pretty strong benefits for using it in library mode as well, embedded within a JVM within your application. Some of those, library mode actually has more features. You've got richer APIs. You can do more things in library mode that you can't do in client-server mode. Client-server mode, the set of operations you have is slightly more limited. Configuration, you can have programmatic configuration. You can directly change the behavior of a cache or any given node if you're running in library mode. You can also extend it and embed it. You can add more things to it. You can add more behavior to an Infinispan node if you're running in embedded mode. For example, you can inject your own interceptors into Infinispan to add, let's say you want to do validation. Every time someone stores data, you want to kick off a separate process to check whether data is valid before it goes in. You can do all that in library mode. You can't do that in client-server. And of course, in many cases, it's faster as well because you're living within the same JVM process. So, okay, there are benefits to that. How are we all doing so far? Am I boring anyone to tears yet? No? No one's crying in the back? Okay, that's fine. So a little bit about, the reason why I said that is because it's actually going to get even more complex now. So if you thought that was deep. Well, I'm going to talk a little bit about the architecture in terms of scalability. Who's familiar with Amazon Dynamo? Who's actually read the paper? Well, yes, it's kind of eye-watering. It's long and complex, and takes about a month to read. But anyway, a lot of core Infinispan design is based on Amazon Dynamo, and the ideas in that. Amazon Dynamo is basically a system for distributing data in a fault-tolerant way on an unreliable network, where no nodes will fail and some nodes will not fail, and a way of actually locating data across a cluster. I'm not going to go into too much detail of Amazon Dynamo, but essentially this is kind of what we use. In terms of scalability, for the two types of scalability first I want to talk about, there are two things you often want to scale when it comes to a data grid. One is you want to scale throughput. What does that mean? You want to actually handle more transactions per second. So you want to add more nodes because you need fast reaction to data. And the other reason to scale is capacity. You just want to be able to store more stuff, right? Your existing servers are full. You just need more space. So the two main reasons for wanting to scale. Now, using Dynamo and using the consistent hashing techniques in Dynamo, we achieve scalability both for throughput and capacity at the same time. Like I said, I can go into more detail. In fact, if people want to talk about it, maybe later on, I'll be around. You can have a chat with me. I can go into more detail. But I'm not going to do that right now because it's pretty deep. So, yes. Durability, that's the next important part of the architecture. So a data grid, if it just stores things in memory, it's kind of useless, right? It's just a cache then. It's just either a single node cache or a distributed cache. But to become a data grid, I think you actually have to be durable as well. You've got to be able to survive restarts. You've got to be able to survive server failure, things like that. And we achieve durability in 3 different ways here. The first one is via replication, where you maintain copies of data somewhere else. The next one is persistence, either to disk or to a database or some sort of persistent storage. And the third one is replication to a different cluster altogether. And that is useful in case to guard you against an entire data center going down, which sometimes does happen. I mean, Amazon's had a couple of high-profile cases where entire EC2 data centers disappeared, and anyone running things on EC2 in that data center just lost everything. But yes, so that does happen. Now, sometimes people use these in various combinations. Sometimes people just use replication and persistence. So it's up to you to pick and choose what you need based on your application and what you need. The first one of those, replication, that's quite simple. It just basically means you make copies, right? So anything you store on one server, a copy is going to be stored somewhere else in the cluster as well. So if that one server fails, you've got a copy immediately, locally, which you can reach on a LAN. It's not far away. Now, the core thing with consistent hashing here is that you store enough copies in the local cluster to be durable, but not too many copies to prevent scalability. Because if you're storing copies in every other node, that's a scalability problem. It means that every time you add another node, you've got one more copy to store. So if you have a cluster of 5 servers, the cost of doing a write is you've got to write 5 times. If you suddenly double that to 10 servers, now your cost of writing has gone up to 10 times. And that becomes a scalability problem. So consistent hashing allows you to do a fixed number of copies no matter how big the cluster gets. So that becomes linearly scalable. Persistence, again, added durability. You persist to disk. You can do things like warm starts. You can shut down an entire local cluster and bring it back up again. You wouldn't have lost any data. So again, useful for that. And some of the architecture around that. So writing through to disk, we support, it's all pluggable in Infinispan. We currently support file system-based persistence, where you just write into a file system. JDBC database as well over a connection. And of course, you can write your own pluggable implementations as well. Now, this slide actually pertains to JDG, to the JBoss data grid, and what we support officially. Now, upstream in Infinispan, there are a whole bunch of different connectors that people have written and contributed for persistence. Things like persisting to Hadoop, persisting to Cassandra, persisting to Amazon S3, persisting to all sorts of different storage engines. So there's some pretty cool stuff out there that you guys can play around with. The next thing I want to talk about is consistency. So who's familiar with Eric Brewer's CAP theorem? Not many? Okay, so I'm not going to talk too much about consistency then, except that this is strongly consistent. Strongly consistent just the way a database would be strongly consistent, right? We actually have mechanisms to do that. Now, this actually kind of goes against what most distributed computing is all about. I mean, a lot of distributed computing kind of says that you can't be strongly consistent and be highly available at the same time, because something's got to give. The moment a server goes down, or you might have transient failures in your network, how do you expect to maintain consistency across the entire cluster? Well, the trade-off usually is availability. That the way to maintain consistency is that if you realize there's a network hiccup, you've got to kind of get the cluster into read-only mode for a bit while you correct and fix it, and then you continue on. So Infinispan is strongly consistent. The reason why we do that, why we pick strong consistency, is is to be in line with databases. Because like I said, the background with Infinispan or with most data grids is distributed caches. Distributed caches usually sit in front of a database. Databases are always strongly consistent. So if a database is strongly consistent, you want the grid to be strongly consistent as well, to have the same consistency model. So that's kind of what we do. And because of that, we can support JTA transactions. We can support full XA, in fact, and we do that as well. So you can even do XA with recovery and everything else. So if transactions float your boat, if you get excited about transactions, this will be good stuff. Not many people get excited about transactions. For some reason, it's not particularly sexy. I don't know why. All right, so I've got a couple of performance-related slides here now. I don't even know why I have these numbers here because, firstly, they're slightly outdated. It's actually a lot faster than that. But I guess the main thing is I just want to show that things are linearly scalable. See, as you increase cluster size, that last one, they shouldn't even be there because that just kind of gives you a weird graph. I'm jumping from 10 nodes to 32, so it kind of makes it a bit confusing. But essentially, you do have a linear progression in throughput if you ignore the last one. The next one is elasticity. So this chart here, which looks like a pretty painting, basically shows you the response times on each node as we take a large cluster and shrink it back down and then bring it back up again. So now in this case, we're starting with 32 nodes. We're shrinking down to 16 nodes in the middle. We're shutting them down one at a time. The entire time, we're just like, we still have a load generator generating load on the cluster. So we can see that there's a linear degradation of performance from 32 nodes to 16 nodes, and that's just because you've got half the number of servers dealing with all the work. But you can see that there's no there's no major stop or anything like that. It kind of goes down. What you're seeing dropping off is that one server being shut down each time, one at a time, until we get to 16, and then we start them back up again, up to 32, and you can see the performance again ramp back up to what it used to be. So. Again, interesting little graphs here on how it performs when you're trying to scale in and back out again. Right. So a little bit about features and what's supported roadmap-wise. So a lot of the things that I mentioned, that's all in what we call JDG 6, the JBoss Data Grid version 6. That's the current version now. We're working on 6.1. 6.1 will be released hopefully early next year by January. Now, a lot of the features that I mentioned here that are coming in JDG 6.1 already exists in Infinispan upstream, right? So the Infinispan version already has all of this stuff. It's just that JDG doesn't yet. The reason why is because we take each one of these features, we put it through a lot more QE and everything else before we actually say we can support it. So, so this is kind of like for the supported version. What we're doing in JDG 6.1, we're adding more supported persistence engines. Like I said, Infinispan's got a whole bunch of persistence engines, like writing through to Cassandra, writing through to S3, writing through to Hadoop, which we don't do right now in JDG. So we're going to start supporting more of these modules. The next one is cross-data center failover. The whole thing about replicating to a different data center. Again, that's upstream only right now. It's not in JDG. That's going to be in JDG 6.1. Hot rod feature parity. So I mentioned that one of the big reasons people use library mode is because there are more features than library mode, right? More APIs you can use. One of the goals is to try and add all of those to the hot rod wire protocol, so you have, whether you're using it remotely or within the same VM, you have the same feature set. So we're trying hard for that. More hot rod clients. Like I said, people have written a C# client. I'm hoping to see more come out. I think a C++ client is pretty close to being contributed as well by somebody. MapReduce and queries, again, they both exist in upstream Infinispan. We're putting them into JDG as well because people want them. CDI and Spring integration for people who like to use things like Spring or CDI if you're running in a Java EE environment. Again, there's lots of tight integration with these two technologies. Makes things very easy. You can annotate methods to say, just cache the result of that method in the grid. I don't want to execute the method every time I call it. You can do some pretty cool stuff like that. I can give you guys some demos later if you're interested. It just makes interaction with a grid so much easier. Makes configuration of a grid so much easier and faster as well. Zero downtime cluster upgrades, again, very, very important feature that a lot of people seem to like. If you're running a data grid, you want to upgrade the version of JDG on it. You don't want to shut down the grid and then upgrade and restart it, right? because that means your application is going to see downtime. If you're running the kind of application where you can't have any downtime, we're going to support doing zero downtime upgrades as well. We can upgrade one node at a time and still maintain data consistency, still maintain availability to your clients. So how are we doing so far? Good. Okay. So, I mean, I'm going to finish up with this interesting slide by some of the smart people at Gartner. Gartner's full of smart people, right? They sit in these offices and they just like make these predictions. They must be really smart to do that. I can't do that. So what they reckon is that by 2014, at least 40% of large organizations will have deployed one or more in-memory data grids. The reason why, I presume, is based on all the stuff I started my talk with about the volume of data we're dealing with, about the need for fast access to data, and the need for businesses to react to that. So that's pretty much it. So with that, I'm going to leave you with some links here. That's the first URL. That's what you're going to use to go and have a look at the JBoss data grid. You can download a copy of it and play around with it. The open source project, Infinispan, that's a link to that over there. If you're interested in joining the Infinispan community, I'd say join us in IRC, the last link over there. And yeah, I mean, you'll find the entire core team on IRC. Just come and say hello. Follow us on Twitter. And I also want to say that we've written a book about it as well. So I've got 4 copies here, which I'm going to give away to some of the most interesting questions, and some T-shirts as well. With that, does anyone have any questions? No? I even bribed you guys, come on. Seriously? Okay, I'll even sign the book. Yeah.
Here's one question from me. What about deployment of this whole big data support system? Because you have plenty of servers on the production, of course. There are many CPUs here, many more memory there, so is some kind of way to optimize the resource utilization?
Are you saying to monitor the resource utilization?
No, the optimize usage of the resources on the production system. So you have to, I don't know, invest into the equal server configuration, or you can, I don't know, set some more data here when I have a big fast storage and then some processing units.
Right now, no. Right now, they're all homogeneous systems, so everything will be kind of equal. But yes, that's been something that a lot of people have asked for, to be able to add weights to certain servers, to say one node should have twice as much data as the other. So yeah, I mean, that's an open request and that's being worked on, but we don't have that yet.
Thanks.
How does this Infinispan compares to other data grid technologies?
Well, we're just better, that's all. What do you want me to say? That's a hard question, because like I said, the data grid market right now, I mean, not the market, but the space, it's a pretty poorly defined space. So everyone's got their own feature sets. There's no 100% overlap in features. Some have some features that others do not. Some have some performance characteristics that others do not. One interesting thing, I don't actually have a slide for this or any links for this, unfortunately. It's a project called Radar Gun that I actually started some years ago. Radar Gun is basically a benchmarking tool for different data grid projects, for products. I actually started Radar Gun to benchmark different versions of Infinispan against it. So, because, I mean, here we are developing new versions of Infinispan, putting more features in it. I want to make sure we're not getting slower. It'd be nice to have new features, but I also want to get faster, right? So I built this tool to automatically run benchmarks against different versions, the same benchmark against different versions on the same hardware. We also use it for different benchmarks on different vendors, like you said. So that might be something that you might want to download and try out and see what works best for your particular use case. Wow, 3 hands went up at the same time. Start with you. Yes.
Are these JSR widely supported by different vendors, like you mentioned Coherence, for example, and so on, so we can hope for one unified way of writing our clients and integrating into J2E and so on?
We can hope, yes. No, I mean, realistically, 107 is quite heavily backed at the moment by a lot of people. 107 is backed by Red Hat, IBM, Oracle, EHCache, GridGain, quite all the major players in the space, except VMware for some reason. And JSR 347 is similar again. I think the only people we don't have backing from in 347 again is VMware. And I think it's IBM are kind of umming and ahhing. They've got some legal issues around that they need to figure out. But yeah, Oracle's there, EHCache is there.
Okay, but do you mean that they are there, but is Coherence supporting this
Yes.
JSR, implementing?
Yes.
So we can use it by these interfaces from this JSR?
Eventually, yes. I mean, they've not done it yet.
They haven't done it.
They haven't done it yet.
And you have done it already?
The 347 is very, very new. Because we're still talking about the ideas to what the interface should look like.
Okay.
So, I mean, for example, there is the Coherence engineers and myself and some of the Terracotta engineers, we're designing the interface together, saying, what should it look like?
Okay, so in the future.
Yeah.
Okay, thank you.
Just please
second.
wait a second.
She can't run that fast. And you don't want her to throw the microphone at you.
Okay, you have said that the data in the cluster is not copied one-to-one to every node in the cluster. And you also showed us that the downtime of one element in the cluster doesn't cause any problem with robustness. How many nodes have to fail down at once to cause some serious problems?
That's configurable. So depending on the size of your cluster and how resilient you want, how durable you want your data to be, you can configure how many copies are stored. And that will affect, again, how many nodes should go down to cause a disaster.
And a second question, how big period of time has to pass until the cluster will notice that one of the nodes is down?
It depends. It depends usually on your network, because the way you detect it is by network heartbeats. If you're having a serious network problem that even the heartbeats aren't going across, yeah, you could have issues where suddenly just everything starts falling apart. This is where eventual consistency comes in, and where strong consistency becomes difficult. But that's an anomaly. Usually, if you're running on a fast network, you're talking of the order of milliseconds to detect a node failing. Yeah.
Okay, thanks.
That's the last question.
So you said there are no master nodes. What happens if the cluster is split in half for some time, and some applications talk with one part, and the other part of applications talk with second half of the...
You're talking about a network partition.
Yes. How do you synchronize it?
Yeah, right now we don't deal with network partitions. If we detect one, we'll shut down one half of the cluster. So, yeah.
Thank you.
I mean, we do have eventual consistency on the roadmap as an option, where we can deal with a network split and have both sides work at the same time, and then merge the data sets at the end using vector clocks as version tools and whatever. But that's not there yet. Right now we're doing a strongly consistent model where if we have a split, we will shut down one half. Yeah. Okay, I think we can take one more, even though she said no more. Don't tell her, okay? It's coming.
What kind of network topologies does DataGrid support?
What kind of network topologies?
Yeah, I mean the ring, the mesh, in a cube, or in a bus.
That is pretty much agnostic, because we're using JGroups to actually take care of the network, and JGroups supports pretty much everything at that point. JGroups, again, very pluggable. It's got lots of different modules for different network types, even for different wire protocols as well, for UDP or what you may call RDMA and things like that. So yeah, there's a lot that we can do there. Now with that, unfortunately, she came back, so she's going to yell at me if I...
One question. Is the Infinispan cloud-friendly regarding multicast and...
Regarding mod cluster?
Multicast and cloud-friendly. You can run Infinispan in cloud currently?
Yes. Oh, that's very simple. All right. Okay, so for whomever who actually asked a question, if you come up, I'll give you a copy of the book and a T-shirt. So yeah, I'll see you guys up here. And thank you for listening.